So we said we'll talk about this problem about photon counting in vision, and so that's what I'll talk about today. And this is entirely based on this discussion by in Bialik's book, chapter 1 and chapter 2. Okay. Okay. So what's the central question? So this is actually one very early problem that people started to think about in this sort of biophysics concept, that what sets the boundaries of our perception, right? So if I'm sitting in a room and you shine a light at me, how dim of a light can I see? Okay, if you reduce the intensity of the light more and more and more progressively, is there a bound where the vision, whatever the neurons and so on in my eye, in my optic nerve, will not be able to detect the light that you are flashing at me? Okay, so that's the question. So people have been thinking about this for a long time, and in particular since after 1905, when the quantum, we realized that light is not a wave, but it is quantized and it is photons. The question then became that, what is the minimum number of photons that our eye can detect? And Lorentz, like I was saying, with the back end of the envelope sort of a calculation around 1910, estimated a number of around 100 photons. And this was just the number of photons that was falling on our eye. Some of that would, of course, before they reach the retina cells, there would be some loss due to scattering or absorption. So in principle, you can think that this number is going to be somewhat lower than 100. So this, in that some sense, sets a bound that what is this minimum number of photons. Okay. But after this, so some time after this, some 20, 30 years after this, people started thinking about how to do this, estimate this quantity a little more quantitatively. And so this is the paper that we'll sort of discuss by Hecht, Schleyer, and Pirenne. This is in 1942. Okay, so energy, quanta, and vision. And again, if you read the abstract, so light is emitted and absorbed in discrete units. Its energy content is h times nu. There is some chemical process that goes on when a photon is absorbed by our retinal cells. And early measurements show that only a small number of quanta is required for a threshold stimulus. So that's the question that they were trying to address, that what is the threshold number of quanta that you need in order to say that, yes, I have seen a light, and so on and so forth. So that's this experimental paper. So just a little bit of background. So you may know from your, I don't know, class 10, 12 biology, that you have two types of cells in our eyes, rod cells and cone cells. In dim light, when light, in a dark sort of room, the cells that are responsible for vision, the photoreceptor cells, those are called rods. Okay, and since we are sort of trying to look at the threshold, so these are the sort of cells that we are concerned with. Okay, these rod cells. So these photoreceptor cells contain a pigment, a photopigment, which is called rhodopsin. Okay, and what that does is that when it absorbs a photon, it undergoes a structural change from a cis to a trans structure. So this is what it sort of looks like. So this is this retinal, which is in rhodopsin, and when it absorbs light, it undergoes this sort of a conformational change. What this conformational change does is that this gets translated into an electric current across this rod cell's outer membrane. This current flow generates changes in the voltage. This voltage causes other ions to flow in and out of the cell. In this particular case, calcium ion flows. And this change in calcium ion flows trigger the transport of vesicles, which contain another chemical, a neurotransmitter, to the cell membrane. So this is, in some sense, a nerve cell. So this is a nerve cell. Okay, and you get these transport of vesicles, and I just say this because we'll talk about this at some point later on, that how these vesicles are transported from one point to another is also a fascinating story. So these get transported on tracks, filamentous tracks, which are called microtubules and actins. So these are not random diffusion, but these are actively transported motion. So these get transported on polymers, which are called microtubules and actins. In any case, so these vesicles flow to this cell membrane. They get out of this cell membrane and release this neurotransmitter. This neurotransmitters diffuse and bind to receptors on the surface of the next cell. Okay. Next cell. and they in turn generate a current of their own. So there's this cascade of chemical changes and currents that get transmitted along cells in your nerve, and finally the brain receives some signal, and you say that yes, I have detected light in that. So that's the sort of chemical machinery in the background that happens when a photon falls on one of these cells. So if I think about this from the statistics point of view, the absorption of a photon by a single molecule is a random process, okay, and that probability is proportional to the intensity. So if you have very intense light, you have a very high probability that you will see that detect that photon. If you have very low intensity, you will have a low probability. But moreover, this emission of photons is also random. Okay, so it's not that this is a very when you have a light source, generally it's not that you have a steady stream of photons at a given sort of interval that is coming out. It's a random process. So that has some statistics to that as well. And what is the characteristics of that random process? In a very small window of time dt. So if I'm thinking about this counting process, in a very small window of time dt, there is some probability r dt that a photon will be counted. And this photon emission is uncorrelated, which means that the events in different time windows are independent of one another. So given this, what sort of a process is this? This is therefore a Poisson process. And we know, we just learned how to describe the statistics of Poisson processes. So in particular, if I ask that, what is the mean count? Okay. What will the mean count depend on for this sort of a process? What is lambda? But here is you're recalling what we derived last day. So here is my definition of the Poisson process. So in terms of these parameters, let us say I've shined a light for some time capital T. Okay, so time capital T. What would the mean depend on? The mean is simply r times t, right? The mean is simply r times t. Moreover, you can also get the distribution, of course. So what is the probability that we obtain a count of n? And that is simply my Poisson distribution, e to the power of minus m, m to the power of n by n factorial. And this mean, from a classical point of view, is proportional to the intensity of the light flash, right? So which is the number of photons incident per unit area, per unit time. Huh? Which one? Of course. So this, you're doing this experiment with monochromatic light, ideally, of some wavelength which is in the visible range. Otherwise, this chemical transformation will not happen. If you think about this classically, this mean is of course proportional to the time, but it's also proportional to this intensity of light, I tilde. And there are some other biochemical factors. Essentially, my eye is not the same as your eye, is not the same as your eye. So there is, how much loss, and maybe if I'm older, my eye is not as good as your eye. So I need slightly. So there is some individual to individual variability. That is all of that messy factors that we don't know is sort of encoded in this parameter alpha. But the essential thing is that it depends on this intensity and it depends on this time. Okay. And this product is what they are calling as I. And so what you can do is that you can sort of give flashes of different intensity, right? Of some particular monochromatic light. You give it for some different times, and therefore you get different means. And you ask that, you ask about this probability. So that's the idea. So this is exactly the experiment that these three people did, this Hecht and the two others whose names I have now forgotten. So they had an observer who sat in a dark room. So in fact, these three people, Hecht, Schleyer, and Pirenne. So if you see the data, you'll see three observers, SH, SS, and MHP. So these are the three authors who did this experiment. They sat in a dark room. They waited for 30 minutes in order to allow your eye to become acclimatized to that dark room. And then they shined a dim light is flashed at them, and if they see a flash, they just record a yes. That okay, I go and flash a light. If they see it, they say yes, and then you record these counts. Okay, so that's the experiment. And the idea is that as an observer, I say yes, I have seen a flash, if I have seen this threshold number of photons, right? So if the number of photons that I detect is larger than this threshold number, I say that yes, I have seen a flash. Okay. And then what the question that we want to ask is that what is the probability that I see a flash of intensity I. So what is the probability that I see a flash of intensity I? It is the, yes. So ultimately you will vary the intensity, but for a given intensity, you do this experiment multiple times so that you have statistics, and you ask that at this intensity, what is the probability that I see this flash of light? So that is the A that we want to ask. What is the probability that I want to see a flash of intensity I? Yes.
Are we using a particular?
How do you mean?
Like
light of some light of some particular frequency or wavelength. Yes. So this is monochromatic light. So I forget what they've tried. They did 3-4 intensity. I mean 3-4 frequencies, but in a given experiment, you shine light of some particular frequency.
So in every frequency, the number of photons changes.
Huh?
So in every like if we are using different frequencies, so the number of photon will also change.
No, so that's the question. That is there some fundamental threshold that you get, irrespective of, as long as it's in the visible frequency, irrespective of the frequency of light that you can detect, that your rod cells can detect.
So, but for example, like if there is a red light, so it's we know that it's used for signal and all, and like low blue light and all, it's good for the light to be spread. So if I am using a red light and a blue light, then what I'm observing, won't it depend upon the frequency?
Correct. So the actual numbers will depend.
Yes.
Okay. So how much scattering there is, for example, at one wavelength or relative to other wavelength, all of that will get absorbed in these factors of alpha. This threshold number k that we are detecting, that you can estimate independent of that wavelength of light. Okay. So that's the idea. So the quantitative values will change, yes, but the idea behind these experiments was that is there some sort of a universal threshold that I can detect independent of the frequency of light that I'm doing this experiment with.
One more thing.
Yes, of course.
Sir, does it also depends upon the vision of a person? Like
again, yes, all of that is in that factor alpha. So this alpha is whatever individual to individual variability that you have, frequency dependence, and so on and so forth. All of that I just put in this factor alpha. Okay. So if you like I said, so if you do for me and you do for you, although let us say both of us have the same k value, the threshold value, the actual plot that you will, the actual probability that you will get, that what is the probability that I detect a flash, will differ for me from you, and that will differ because this factor is different in principle, okay? And that has to do with all of these other extra factors. So the question is then, I shine a light of some intensity, okay, I, and I ask that what is the probability that I see this flash essentially, and what is this? I just flashed it actually. Yeah. What is this? So in general, of course, I know that because this is a Poisson process, this number of photons obey this Poisson distribution. So I know that what is the probability distribution n given a mean intensity, and the mean intensity is like alpha times I. But how do I go? So this thing is what I know, and that is this Poisson distribution in the previous slide. But how do I go from here to here? If I'm saying that I have a threshold intensity k, a threshold number of photons k, not intensity, sorry, then how is this probability that I see this flash related to this probability of n? Exactly. So I sum over all n values which are greater than or equal to this threshold, right? So that tells me that this is the probability of seeing this flash. Okay. So that is whatever this summation over k equal to n equal to k to infinity. So you can think about how this curve looks essentially for different alpha or for different k, and it turns out that what this threshold k does is that it changes the shape of the curve, whereas the parameter alpha translates the curve essentially. So it is just plots of this function. So if you look at k1, k3, k10, what it does is it changes the steepness of the response. So this on the x-axis is light intensity, and on the y-axis is probability that you see this flash. Okay? If you have very low intensity, you mostly don't see. If you have very high intensity, of course, you see definitely. Somewhere you go through this switch-like response from 0 to 1. The nature of this curve is controlled by this parameter k. What this parameter alpha does is that it just takes this curve and pushes this way or that way. So, for example, this curve over here and this curve over here are the same case, k equal to 3, but two different alphas. So, it has just taken this curve and translated it along the x-axis. So, this is the experiment that now they are doing. They flash this light of different at a given intensity many times, so that you find the probability of seeing a light at a given intensity, and then you vary the intensity, and then you plot this curve. So, that is the experiment. So, this is experimental data. So, these are the three authors, SHSS and MHP. They tabulated at every frequency, so at every intensity, what is the frequency or the probability that they observe the flash, and then they plotted this. And what they see is that if you plot, these are the three authors, so if you plot this, the probability versus the mean number of photons or the intensity, what you get is a very nice fit to this curve, to this expression, this p probability of seeing, for a threshold value of k equal to 6. So, then what they say is that you need roughly around 6 photons to come and be incident on your retina in order for you to say that yes, I have seen a flash of light. But what that means is, so of course, when I say that light is falling on my retina contains hundreds of these cells, right? So, the fact that I only need 6 photons means that it's extremely unlikely that any individual photoreceptor cell needs multiple photons, right? So, therefore, what we are saying is that you have these individual photoreceptor cells which can generate reliable responses to single photons. The structural change and this cascade of chemical changes, electric currents and transport that happens, that translates this signal to the brain. You can generate these responses at a reliable level just in response to single photons. In that sense, it's a very beautiful biophysics experiment. It talks about what is the sensing limit in that sense of our rod cells, and the sensing limit is set by quantum mechanics in some sense, in that you detect 1 photon essentially. So, I don't know the details, but the way this is in principle done. So, if you would have 3 observers, right? So, you would have observer 1 and let us say observer 2 and I don't know, maybe observer 3, something like this. Okay. In general, why would you have 3 curves like this? You would have 3 curves like this because you are doing 3 individuals, right? Therefore, they would have some alpha 1, alpha 2, alpha 3, right, in general. So, unless you are really lucky that you have 3 individuals who have the same effective alpha parameter, which you would be unlikely to see this. So, this is actually corrected for this alpha change first. So, if you just do if you were to do it for 3 individuals and do a naive averaging, you would get, I don't know, you would get some different curve. The average curve would actually produce a different k. So, if you are trying to estimate what is the threshold number, you would actually have to correct for these individual alpha variations and then average and find out what is this correct k, the correct threshold. So, this data is corrected for this alpha variation. How is alpha varied? It is not up to us. So, essentially, like I said, so it is some parameter which encodes all of this, how good is my eye compared to your eye and so on. So, it's not really varied. It's just that you're doing an experiment for 3 individuals and they would ideally, they would, or rather in reality, have 3 different alpha values. That earlier curve that I was shown, that was just a theoretical curve. You just plot just to see what alpha does essentially. But in the experiment, each individual will come with their own alpha. Therefore, when you're trying to find out what is the actual k, you would have to correct for that alpha variation before you do this averaging. Otherwise, the averaging will give you wrong results. Okay. So, that's what. So, I don't know exactly how in that experimental paper they did it. I think ideally what I would assume is that you fit each individual curve to an alpha and a k, and then choose a common alpha to plot this sort of some reference alpha to plot this sort of a curve, so that you can estimate the best k fit. But I don't know exactly. I would have to go back, or rather, one has to go back and look at the paper. All right. So, moving on. So, like I said, this chemical changes in this photoreceptor cells generates currents. So, So the previous set of experiments were, done on human subjects. So you sat in a room and you looked at light flashes. But now, can you take these single cells and say something about, what is the sensitivity of these single cells to individual photons? Okay. So these are experiments done, of course, much later, because the technology was available much later. So these are experiments in around 1998. And what you see, so these are in vitro experiments. You extract a single rod cell in a laboratory, you shine a light pulse on it, and then you measure current flows. So this is, for an example, experimental trace, where you provide a light pulse at these locations, so wherever these bars are, and you see how the current across this rod cell that varies. So whenever you give a pulse, you get some sort of a response, a change in the current. One thing that you would note is that the responses again is not deterministic. So you are shining the same pulse, does not mean that you are getting exactly the same output current trace. So there is stochasticity and there is noise. One source of noise is that there is always background fluctuations in the current, right? So the cell has this membranes. So the cell, so whatever, I have some cell, it is covered by a membrane. Ions flow in and out of the cell. So there is always some sort of a current flow. Because again, even these ion flows are stochastic processes and so on. If you look at a resting cell and if you trace the current, trajectory as a function of time, there will be fluctuations. Okay, so and that fluctuation is this sort of a background fluctuation that you see when you are not shining light. Even otherwise, so for example, here somewhere I have shined. I have shown a light, shined the light. But I don't really see that much of a response. Okay? So you're not guaranteed that just because because again we are shining they were shining very dim light, it's not guaranteed that you'll see a response. Sometimes maybe no photon that is not enough to generate a response. Sometimes you'll generate a single photon response, which is roughly of the order of 1 picoampere. Sometimes it will absorb 2 photons and then you'll generate a larger response, something like this, multiple of 2. So again, here is the experiment then that they did, that they expose a rod cell, again an in vitro experiment, to a dim flash at some time t equal to 0, and then you measure the current flow. Okay. You do this many times. In this particular case, they did it 350 times. Okay. So every time you shine a flash of light, what you see are traces like this. So this is the current as a function of the time after the flash. So time 0 is when you have flashed the light, and sometimes you'll get no response. Sometimes you'll get 1 photon has been excited, so you'll get something roughly 1 picoampere of response. Sometimes maybe 2 photons were absorbed, and you'll get somewhere around 2 picoamperes of response, and so on. Okay. So it's a stochastic process. Although the light that you're shining is the same, the response that you get is random. So what they did was that, or what one can do is that you can, for example, for each signal, for each flash, you can determine the time when your current takes the maximum value, okay? And then you plot the distribution of these maximum currents. Okay? And if you were to do that, so these are sort of the raw experimental data that I extracted. So this is the current at peak whenever it reaches a peak, and this is the distribution of that current. So the question is that, can you sort of understand this distribution using basic probability? Okay. Can you say what this distribution is going to be? So what I want to estimate again now is, what is the probability distribution of these currents, P of I, right? Okay. So before I start, so like I said, so even if there is nothing detected, there is always some background current and there is always some fluctuations around that background current. So how do you treat those fluctuations? So if you plot the distribution, you'll see that these fluctuations are roughly Gaussian, around 0 mean, because that's no response, but with some variance, which is, let's say, sigma naught square. Okay. So you can do that by, you can estimate what is this sigma naught by, again, just looking at these fluctuations. Looking at these fluctuations in the experimental data, plotting the distribution, fitting it to a Gaussian, extracting what is the variance. When there is no photon that is observed, you get some Gaussian with mean 0 and some variance sigma naught square. if you have absorbed a photon, then of course again there will be some fluctuations. Assume that this fluctuation has some. So if you have a single photon that has been absorbed, then the mean intensity or the mean current is some I1, and there is going to be some variance around that as well. So again, you assume a Gaussian with mean I1 and variance sigma 1 square. So these are the two things. And then what we want to ask is this question, that what is the expected probability distribution of currents P of I? So we can ask that, what is the expected probability distribution of currents if no photon was absorbed? So n being n equal to 0, n is the number of photons. If I say that if no photon is absorbed, what is the probability distribution of currents? What is this probability? Yes, Samarpita? What is this probability? P of I given n equal to 0? It's just written in the first line. It's a Gaussian. So what would that mean? So what expression should I write? One by root 2 pi sigma square. What is x? What is n? N minus 0. I minus 0, right? N is the 0 number of photons. The intensity that the current that you observe is I. 2 sigma square, right? I square. Okay. So I know what is the probability of current I, given that I have observed 0 photons. Okay. Now, similarly, I could write down what is the probability of a current I if I had absorbed 1 photon. Okay. And what would that be? So this is, I call this sigma naught. So what would that be? Two pi sigma 1 square e to the power of by 2 sigma 1 square. Okay. So now just a subtle issue. So when I define this sigma 1, it is essentially the variance in a single photon response, which means that I absorb a photon, I produce some current in response. What is the variability in that? But that variability is essentially superimposed on a background, which also has some distribution and some variance. So, and which is independent of this photon distribution. So essentially, if I have two distributions, one of variance sigma square, normal with variance sigma square, another with variance sigma 1, what would be the variance of the effective distribution or the total distribution? So if I have some sets of random variables, let's call it fj, j equal to 1, 2, so on and so, and each of this has some mean fj, and it has some variance sigma j square. And if I were to consider the sum of these random variables, sum over j fj, and then I want the mean of the sum and the variance of the sum, how are these related to the individual means and the individual, provided these random numbers are random variables are independent of one another, how are these means and the variances related to one another? And variance? Variance? Root over? So square of the variances. The variances. square of the standard deviation sigma. So the variance is the sum of the variances. So the variance is simply sum over j sigma j square, and the mean is also sum over j. Okay. This, does everybody know that if you have independent random numbers, that the variances are the sum? If you don't, you can just take this expression, define the variance of this, and work out that if these are independent, these cross terms will cancel each other, and you'll be left with the sum of the variances. Okay. So in that sense, so having said that, therefore, should I modify this probability distribution? What will be the variance of this? Because this is the background signal plus the single photon response. So therefore, sigma 1 square plus sigma naught square, and here also sigma 1 square plus sigma naught square. What is the A? So this is right now what I am doing is theoretical calculations. So saying that I know I have fluctuations in the background. So when no photon was detected, something was fluctuating around 0. And I say that, well, I'll describe this by a Gaussian with mean 0 and variance sigma naught square. If you wanted to estimate what this sigma naught was, you would have to go back to the experimental data and estimate. But as a treatment, this is just I'm saying that the fluctuations are distributed normally, even in the case of no photon and in the case of when one photon has been absorbed. If I wanted to estimate these, of course, yes, I would have to go back to the experimental data and look at the fluctuations. Of course, because this is a mean, right? Sigma also contains the
Sigma 1 that we have declared for single photon response. That contains the background response as well.
Right. So think of this, I will come to, so it's a good point. So think of this right now as a idealized process. So let us say it has some variance sigma 1, let us say it has some mean I1 for single photon, and in the case of no photon, let us say it has some mean variance mean 0 and variance sigma naught. We'll go back to the experimental data and see what that means. If I wanted to actually estimate what this sigma naught and sigma 1 is. In principle, you're right. The experimental data is a combination of each of this. Okay, so this is probability of observing a current I given that a single photon has been observed. Similarly, I could write down in principle what is the probability that I observe a current I given that I have observed some general n number of photons. Okay, and what would that be? Square root 1 by 2 pi. What would come here? What is the effective variance? But the single photon absorption process, I assume, is independent. So if I am absorbing n photons, it's like absorbing n single photons. So therefore, I'll just write this as n sigma 1 square plus the background variance sigma naught square. Okay? And e to the power of minus I minus n I1 whole square to n sigma 1 square plus sigma naught whole square. Okay. So I've written down all of these conditional probabilities. P of I given this full set of n's. So you are shining a flash of light, a dim flash, but a flash nonetheless. So you are not controlling how many photons are coming out. That is a Poisson process because it is coming out with some rate. So maybe 0 is coming out, maybe 1 is coming out, maybe 2 is coming out. You don't know. Like you saw in that current trace, the peaks are not the same, which means that the number of photons that is coming out is a random process, and in principle infinity with a very low probability. Okay. No, so firstly, this is, like I said, this is an in vitro experiment. So this is not a human subject. It's a single rod cell on which you're shining a light source. Okay, so it's a single cell experiment in that sense. And so here you have your cell, the question, and you're hitting it with quanta of light from this light source that you have. Because this is the emission of light is a stochastic process, the number of quanta of light that is coming and hitting your cell could be 0, it could be 1, it could be 2, it could be 3, and so on and so forth, distributed according to a Poisson probability. Accordingly, the number of photons that comes and hits, you will get some response. Okay, so does that answer your question?
So it means that we are saying that we need minimum 100 photons to see that there is a flash of light. So does it mean that the altogether 100 photons are coming together and I'm seeing it?
No, so okay. So firstly, in that sense, what we said is that if we computed the threshold in the previous A, it was around 6, 7 photons, right? In order to see, not 100. But therefore, what we therefore guessed is that because the retina contains many hundreds of cells, that therefore each cell is at most getting probably 1 photon, and only 5 or 6 of these cells getting hit with a photon is enough to generate a response. But the idea is therefore that each cell can detect a single photon, and now we are going and testing that not we, the authors are going and testing that hypothesis in vitro by using a single cell. All right. So now I have all of this, P of I given n equal to 0, P of I given n equal to 1. What I want to calculate is this, P of I. P of I. So how do I do this? Sibgat, what is P of I? I have all of these probabilities written down, the conditional probabilities, right? I want what is probability of observing a current I. What is that? What is the expression for that? For a product of, so tell me, P of what? P of I. P of I given n. Probability of then sum over all n. Is that clear? All right. So now P of I given n I have, because that is what I have written down. What is P of n? Poisson, right? So it is e to the power of minus n bar, or whatever I was calling n average to the power of n by n factorial times P of I given n, sum over n equal to 0 to infinity. And because you know how long you're shining your light for, you have an estimate of what is the mean intensity of light, or what is this mean average n. This P of I given n is whatever over here, and then you can plot this distribution, right, as a function of the number of photons that are observed. So this is this distribution, I think, n bar to the power of n, n factorial e to the power of minus n, and so on. Okay. So this is this P of I that we now calculated, and the question is that we had this experimental data of these current distributions. How well does this distribution fit the experimental data? So here are those points that I showed, and here is now this curve. This gray line is that curve essentially. The gray line is this function over here. So if I draw this gray line on top of your experimental data points, see here is what it looks like. So you can estimate what is this probability density of what is the probability of observing some current I, purely from this very simple sort of argument based on probabilities and independent random numbers and Poisson distributed processes themselves. Okay. Now, to come back to your question, if I now wanted to actually go and think about how to estimate these variances, sigma naught and sigma 1 and so on, right? So over here you see is the current 0, which means this response corresponds to, or this peak corresponds to the case when no photon was detected, right? So if I were to fit an effective Gaussian to this, of course the mean is 0, but I would get some sort of a width which would give me sigma naught, right? Now if I see each subsequent peak, and again if I fit individual Gaussians, which are these yellow lines over here, the peaks would of course go as integer multiples of whatever is the A, but the variances, you see it gets broader for this and then more broader for this, because this variance is sigma 1 square plus sigma naught square. This is 2 sigma 1 square plus sigma naught square. Once you know sigma naught, you can estimate what is the sigma 1 variance, but each individual distribution contains the combination of variances because of the background intensity and because of the single photon absorption. Why is because so this has to do with what is the intensity of light that you are shining, and they were shining very dim flashes of light. So, the probability that you observe no photon is higher in this case than the probability that you observe one photon, and so on. You're shining a flash of light, right, on your rod cell, and the intensity of light that you are flashing, or the time that you are flashing this light for, is small enough that you are actually most of the time. What is this probability saying? That most of the time it is not detecting any photon, which means that this light is of very low weak intensity, such that you are most of the time not emitting any photon or not detecting any photon. But if you were to shine a very strong intensity light, of course the relative weights of the peaks would change. Having said that, so here is the distribution. Now one could ask that, well, okay, so what I am seeing ultimately is some current. Okay, so I'm seeing some current value. When I do this experiment, I look at the, if I think about those individual traces that I had, something it looks like this, maybe sometimes it looks like this, sometimes it has some peak and whatever. So I look at these individual traces, and what I'm doing over here is looking at the current at the maximum value, wherever that is. Okay, and I want to say that, and I want to ask that, well, have I detected a photon or not? Okay, or has this rod cell detected a photon or not? So in that sense, the next step that you might want to go ahead and ask is that, so now one is thinking about these rod cells as single photon detectors, right? You shine a light and you ask that, have I detected a photon or not? How would you go about doing it? So you would construct some threshold. Ideally, you would say that, well, I have observed some current I, okay, at that peak time, wherever that peak time is after you flash your signal. And then I would like to set some threshold such that if this current I is greater than something, I'll say that yes, I've detected a photon. If this current I is less than the threshold, I'll say that no, I've not detected anything. Okay. Because always there is some noise, right? So you have to be sensitive to this question of noise. Okay. So what we want to do is that we want to set a threshold current such that we minimize the probability of making an error in the single photon detection. So I want to minimize this error that I make, and I want to choose my threshold. So essentially, if I go back to this curve, I have this probability distribution. I want to choose some threshold. Okay. So what is this? What is the current that distinguishes a zero photon detection from a single photon detection? And how will I go about choosing this threshold? I'll choose one of the ways is to do this sort of a maximum likelihood interpretation, where I set a threshold such that I minimize the probability that I make an error. So let us say I have set some intensity threshold I equal to theta, okay, such that if my current is greater than this theta, I will say I have detected a photon. If this current is less than theta, I will say that I have not detected a photon. Okay. So what I am looking at is the probability that I am making probability of making an error. Okay. So let us say that there was no photon. So let us say that there was no photon, but I have detected one photon. Okay. So let me call whatever some notation that I've detected one photon, given that there was no photon. What is this? So this is the probability that I have a current I, given that there were no photons, and because I've detected a photon, it means that this I is going to be greater than this value theta, right? So I equal to, actually, sorry, this is not a discrete, this is a current. So okay, I can also do the reverse error, in that maybe there was one photon, but I have detected 0 photons, right, again because of fluctuations. So this is the current distribution given that there was one photon, and then I integrate over I all the way from minus infinity to theta, right. This is the reverse error. This one. So when you have no photons, right. So let me go back and look at the distribution again. So when I have no photons, so let me forget about these subsequent peaks. Okay. So let me say there was no photon that is detected. You get some current distribution that has some spread. Okay. Now, let us say I have set a threshold current at 0.5. You still have some non-zero probability to observe currents more than that, even though there was no photon detected, simply because of the noise, right. So, what this that is this probability, that what is given that there was no photon, what is the probability of current I where this I lies above your threshold value, because these fluctuations can be large. If you look at those traces, sometimes look at some of these traces, some of these fluctuations can be pretty large. So, that is why. So, when one is interpreting biological data, one has to be a little careful, because noise plays a crucial role, and how you interpret quantities in the presence of noise is actually a central challenge in biology. So, this is what I want to do. So, this is the first part, that there was no photon, but simply because of fluctuations I observe a very high value of current, and therefore, I say that I had actually one photon. So, that is this error. The reverse error is this, that I actually had one photon, but again because of fluctuations I somehow generated a small current, and therefore, in my detection scheme I have said that there is no photon. So, these are the two errors that I have. And then the cumulative error in that sense is the sum of these two. So, if I write the probability of error is P of D equal to 1 given n equal to 0. Either of this is a mistake. So, P of D equal to 0 given n equal to 1, but also this, right. So, times the probability that I actually have n equal to 1 and times the probability that I actually have n equal to 0. Okay. So, these are the conditionals that I detect 1 given that I had 0 photons. So, I have to multiply that by the probability that I have 0 photons, and here I have to multiply that by the probability that I actually have n photons, and these are again whether I have 0 photons or whether I have n photons is Poisson distributed. Okay. And then what I want to do is that I want to choose my threshold. So, remember this is now a function of theta, because theta comes over here. So, this is a function of theta, and what I want to do is that I want to choose my threshold such that I minimize this error. So, I want to do dp error of theta d theta and thereby choose the value of the error. That what is the best threshold that I can choose such that I minimize this error. Okay. So, let me see, P of 0, probability of having 0 photons, times theta to infinity di P of I given n equal to 0. Let me say n equal to 0 since I have multiple quantities, that is one term, and then I have P of n equal to 1 integral di minus infinity to theta minus infinity to theta P of I given n equal to 1. Okay. And I want to take a derivative of this d d theta of this, right. What is this? If your variable occurs in the limit of the integration, then P of n equal to 0 times what? Come on, this is basic Leibniz rule. P of minus, so minus P of I equal to, so theta essentially, theta star, so whatever. Anyway, so let me take the derivative first. So theta given n equal to 0, that is minus, plus a P of n equal to 1 times P of theta given n equal to 1 is equal to 0, right. So essentially at the correct threshold, at the critical threshold, what you will have is these two terms being equal at some theta star, and if you choose this theta star as your threshold, what you will end up doing is you will minimize the error in your detection scheme. Of course, you will still, it's not that you get rid of errors. This is just to minimize errors, but you can never set your error to 0 simply because you are guaranteed to get it small, but you can never quite get it 0 because of fluctuations. And if you, having set a threshold, you can still ask that. So having set this threshold of some theta, you could still ask that if I have observed this current, if if I have observed this value of current, then what is the probability that I have 0 photons? And so essentially you can, if I again go back to that distribution over here, this error, irrespective of how carefully you set your threshold, this integrated value, the area under the curve to the right of the threshold, is still your error probability, right? Because you'll still have events there which will contribute to the error. So in this case, for example, in this case, if you said so, these lines actually correspond to these error thresholds done by estimating this by minimizing this error. So the single, the no photon versus single photon threshold is somewhere around 0.5 picoamperes. And if you then estimate, so if you then estimate that what is the, so again, so this is just that. So if you estimate how much you still, how much of the curve still falls outside your threshold, and therefore what is the error, you'll see that the error in this case is roughly about 3%. So ideally, if you were using these rod cells as photon counters, the single rod cells as photon counters, these are near perfect. If you did an experiment 100 times, roughly 97 times, you could say with accuracy that whether you had detected a single photon or not. So the limits of, so the essential message of this part is that the limits of detection are set by the single photon. It is not the rod cells are perfect, go as far as physics allows them to go, and in that they can detect single photons and they produce measurable changes in response to these single photons. So having hopefully given you a flavor of why noise in that sense is ubiquitous in biological systems, and why thinking in terms of these probabilities allows us to extract information, physical information about these biological systems. What we'll now turn to do is to sort of explore this a little more formally from the next day onwards. I'll start with an example of E. coli motion, but then I'll use that to sort of set up the formal structure behind this sort of a probabilistic approach. Okay. Yes. So whatever I taught today is from Bialek's book. That's true only for today. So next day it will not be Bialek's book. Okay. Anything else? Yes. No. So that's the idea. So what they tried to show was that, again, it's not that there is no variation, but what they showed is that this value of k that they could ascertain to the best of their ability lied in a very narrow range in that sense. So, maybe 5 to 10 or something like that, but not a huge difference. So if you were to do it for some individual, you would not get a k value of 100 or 200 or something like that. That other parameter alpha could vary, but this threshold, that seemed very, very nicely robust. All right. So I'll stop.